Hello. So thank you very much for giving me a chance to be here. It's a great place and scientifically very interesting. I would like to talk about a line of work which is about extensions to monadic second-order logic with this. It's a special quantifier that we've, together with some people also present here, we've been studying. So some of the people involved in this and indirectly also are, there's Thomas, there's Denis, there's Nat, Michał, who decided not to come to my talk, there's there's Laure, and I'm sure I'm skipping others. So what is this U quantifier? It's the following quantifier, well, it's U. It binds a set, so it's a property of sets. It doesn't say that a set exists or that it's for all x, but it says that the property is true for sets which are finite but arbitrarily large. So you can think of the U quantifier as just being this infinite formula that for every n there exists a set x which has size at least n but is finite and satisfies phi of x. So this is the U quantifier, and you add it to, you can add it to MSO, so you can mix it with normal quantifiers and see what you get. And this is the topic of this talk, and this is the logic that I've been studying for 10 years. It's a 10th anniversary. And so first of all, it doesn't make sense to have U if you're working on finite structures. Yeah? If you're working on finite structures, then it's just false. Okay, so every formula of the form UX.phi of x can be replaced by false, and this does not contribute to the expressive power. So this is only makes sense if you're talking about infinite words, infinite trees, or maybe infinite graphs, and that's where it's going to be studied. Okay, so I give you maybe some examples, and maybe so first of all, let's observe that it's more powerful than MSO. Already on infinite words, and here's an example. This is a more or less canonical example. You look words where there's infinitely many A's, but the size of the blocks of B's grows and grows and grows. Okay? So you can write it like this. It's words, there's a certain number of B's and A, a certain number of B's and A, and so on, such that the lim sup of the n's is infinity. Okay, so this is a typical thing that you can define here. Well, you write, essentially you just write this thing using language of logic. So unbounded size for sets X, which are connected blocks of B's. Now this language is non-empty, so I don't know if you have 1, 2, 3, and so on, you can have such a word, but it does not contain any ultimately periodic word, so it is not MSO definable, because every MSO definable language of infinite words has to contain at least one ultimately periodic word. So this is a typical witness that you get more, and it's a question, how big is this? I mean, how much more we can say, and in certain measures it will turn out that this is very big, that it's significantly more expressive than MSO. So why study it at all? And I mean, what's the connection with automata, and what's the connection with this workshop? So is it recognizable? Now, it's a bit of a philosophical question, and I'm not sure what the answer is, but at least I tell you this, it's not obviously no, okay? It is maybe recognizable, and here's the reason why it is at least a little bit recognizable. It is because, at least as long as finite words are concerned, there's finitely many types. That's the idea. So, like for automata, for every finite word, there's finitely many types, then this is a little bit true for MSO+U. And in what way it is true, I will say right now. So suppose that I have a formula of MSO+U, and it has quantifier depth k, and quantifier depth means you count both quantifiers, you don't care which one is U, which one is exists. I claim that from the perspective of phi, there are finitely many different types of words, in a sense that I will make precise right now. So Suppose that I have two words, I mean, not necessarily of length 4 and 3, which satisfy the same MSO formula, so not U, of the same quantifier depth, okay? I claim that if they satisfy the same formulas of MSO, I will just claim it, I will not prove it, of quantifier depth K, then they are indistinguishable for this formula in the following sense, that if you swap this word with this one in any environment, then this will not affect the true value of the formula. So from the perspective of an MSO+U formula, there are finitely many different types of words, because it is well known that for a given quantifier depth K, there's finitely many different formulas up to equivalence. So if you just look at a piece like this, there's only a finite number of types of things that you need to know. So in this sense, it's recognizable. What is not true is that you could do this infinitely often. Now, do this infinitely often is not a very precise statement. So if you had just two words, and infinitely often you replaced the first one by the second one, you could do that. That's still okay. But what you could not do is if you have two equivalent words and two other equivalent words and two other equivalent words and so on, and you replace them in parallel, then you cannot do that. So it's a little bit subtle, but at least in some ways it's recognizable. Okay? And the slogan is that the non-regularity or non-recognizability of MSO+U is only seen in the asymptotic behavior, not in the prefix parts. So here we're exchanging a prefix. So it says that it's prefix independent up to finitely many different colors, like it is the case for Büchi automata or MSO, normal MSO. However, the asymptotic behavior is not finite state, and it is something that we're trying to understand and we haven't understood yet. And there's a lot of work on this, and for instance, Thomas has some new ideas with asymptotic logics, and it's just understanding asymptotic behaviors is something that we're working on. And this work here can be seen as this program. So Büchi condition or parity condition is very simple asymptotic behavior. But there are other asymptotic behaviors which still might be tractable, and we're trying to understand that. Okay, so that's the unbounding quantifier. So I have one new quantifier that I add to MSO. And then what can we say about it? So I summarize the main results that I will talk about today. The first one is a relatively old one, which says that for infinite words, MSO+U is decidable. Maybe not all of MSO+U, but a certain fragment which is positive in a certain sense, which I will make precise. So there are fragments which are known to be decidable. Another fragment that is known to be decidable is that if you take the weak fragment, so you quantify over finite sets and you have U, and then this is decidable and without any positivity assumptions, both for infinite words and infinite trees. And this is another line of work that I will try to tell you a little bit about today. Then here's a very new result, which I don't know what it means for this research program. Is it good or is it bad? But it says that over infinite trees you have difficulties. It says here is not decidable. It's a little way of masking the fact that it's not really undecidable, but you will see what that means. But it's not decidable as well. Okay, I will make it precise in a moment. So there's problems for infinite trees, and an open problem is what about infinite words? And personally, I have no idea. I don't know. It's which way it will go. So there's still a lot of stuff to understand. Okay, so let me begin with the positivity parts. So what is it? So the language that I will talk about are called omega-BS regular languages, and this is something that we did together with Thomas Colcombet. So what are these omega-BS regular languages? And they are defined by an automaton model. So suppose you have a non-deterministic automaton, and it has finitely many counters that it can manipulate. But you have the following operations on the counters. You can reset a counter, so the counters store integers, natural numbers. They begin with 0. You can increment them, and you can reset them back to 0. What is very important here is that you cannot decrement them. And that means that there's very little or no arithmetic available. So for instance, if you have, say, a vector addition system, you can decrement them, and then there's the implicit assumption that if your counter drops below 0, your run dies, and that allows you to do a little bit of counting, so you can do things like A to the n, B to the n, stuff like that. This you're not going to be able to do here at all, because you can just, every run can be prolonged. And so what is the purpose of these counters if you cannot do anything with them? They're basically just output things to them. The purpose of these counters is to produce numbers which will be used in the acceptance condition. So the acceptance condition is as follows. A run of this automaton is accepting if every counter is reset infinitely often. And now if you look at every counter, then you have its value when it was reset for the first time, its value when it was reset for the second time, and so on. You have numbers. So the automaton implicitly produces numbers through these counters. And then the acceptance condition is defined in terms of these numbers. So there's two types of acceptance conditions that you might consider. The first one is that you require these numbers to be bounded. So lim sup is smaller than infinity. Okay? So that means that that the counter is just has bounded values throughout the run. And this acceptance condition is called, it's a very stupid name, omega b. And there is a dual condition, which is you look at these numbers and they have to tend to infinity. Okay, so they grow. Not only do they grow, but you have no subsequence which is bounded. It just tends to infinity, what this term means. And this is another stupid name which we came up with, and it's called omega s, because at the time when we were inventing it, we did not realize that there's such a thing as tending to infinity. We just thought, oh, this is a new behavior of number sequences that we've discovered, you know. They're unbounded, but they have no bounded sequences. We called it strongly unbounded. And I apologize. Okay, so this is the kind of automaton model that we have. So you have counters which are just used to produce numbers, okay? And the acceptance condition is about the asymptotic behavior of these counters. And it's very important that it's a non-deterministic automaton. Okay, and what can you have? So the first class of automata is called omega b automata, and these are automata where all counters have the omega b acceptance condition. So a word is accepted if there exists a run such that, and a number, which depends on the word, such that all counters are bounded by this number. And for different words, it's different bounds. Then the dual class is omega s automata, where all counters have an omega s acceptance condition. So all counters have to tend to infinity. And there is the intersection, which happens to be exactly the same thing as MSO. So if you can be defined by an omega b automaton and you can be defined by an omega s automaton, then you are defined by a Büchi automaton and therefore MSO. This was proved by Michał Skrzypczak. One way of proving it was done by Michał. And what is the most important thing is this. This is the main result that we had with Thomas, which is that if you take a language from here and you complement it, you get a language from here. And vice versa. If you take a language from here and you complement it, you get a language from here. And this is not obvious. Because if you complement a language here, what does it mean to be a complement here? It means that for every possible run, there does not exist a bound. So you have a universal big quantifier, every possible run. And now you have to convert this into a non-deterministic automaton to exist a single run such that blah, blah, blah. And there's a non-trivial construction here, and which follows more or less the shape of Büchi's complementation proof, where he used the Ramsey theorem. But here you have to use more things. And it's rather challenging, and some of the combinatorial ideas that were here were then further developed by Thomas into the theory of cost functions, but there's much more in cost functions than just this. Okay? And so here's one observation. Let's look at this class. This class will have symmetric properties. It's closed under union. It's a non-deterministic model. It's closed under conjunction, and because it's natural. It's closed under you just run two automata in parallel. Nothing big here. They have more counters. It's closed under existential set quantification because it's a non-deterministic automaton. It's closed under U it's not very difficult to see. More or less the idea is here that you have an acceptance condition which says that things grow to infinity, so you can sort of exploit that to show that you're closed under U. It's also closed under universal quantification. This is not obvious. But it's true because this class is closed under existential quantification. So therefore, by duality, this one's closed by universal. And the same thing will hold here. So it's almost MSO+U. So what's missing? What's missing is the dual of the U quantifier you don't have here, which is more or less there exists a bound on the size of sets that capture something, and this you don't have here. So that's why this class is not full MSO+U, and neither is this one. That's why I mean certain positivity, so U has to have the same polarity in the formula all over, and that's the class of languages that you get. Okay? And then you have a class that's maybe an, as my supervisor Igor once used this expression, is an accident of the syntax. So just something that, once you have a syntax, you can just write it, so you write it. It's omega bs automata, which is automata where some counters are omega b and some counters are omega s. Apart from being able to write it down, it doesn't have any good properties, this class. It has decidable emptiness. So all of these automata have decidable emptiness. But that's more or less the best thing you can say about omega bs. In particular, it's not closed under complement. Because if it were, then it would be MSO+U, because it's not difficult to show that this is closed under U, and it's closed under existential quantification and under positive Boolean combinations. So that wouldn't, if it were closed under complement, then it would be all of MSO+U, which it is not, as we shall see in some time. Okay, so that's this class of languages that we did. This is from a 2006 paper with Thomas Combin. And as I mentioned, some of the ideas were further developed by Thomas and his collaborators into the theory of cost functions, about which you will hear more tomorrow. And a cost function is a function which is on finite words, but it gives numbers. And there's a very nice theory, and it's also for trees and other objects as well. But this is not what I will talk about. Another thing that I'd like to mention in this context is that both cost functions and this MSO+U logic have a very nice and rich interaction with profinite words, which was the topic of Szymon Toruńczyk's PhD thesis, and there's a lot of interesting things happening there. Okay, so the typical reason why you want to have profinite words is that, as opposed to finite words, there is a profinite word which has arbitrarily large length, and this is the kind of things that you might want to study. Okay. So that's for the positivity. Now I will tell you a little bit about the weak fragment. So there's a series of results about weak MSO+U. So now you can only quantify over finite sets, and you have the U quantifier. And this turns out to be exceptionally well behaved. So all of them are decidable. And maybe I make a little point that's not completely obvious. When I'm talking about a weak logic, say on infinite words, I'm talking, and I want to decide it, I mean satisfiability. So I have given a formula of the weak logic over some input alphabet, and I ask if it true in some word or tree over this alphabet. And that means that there's an implicit outermost non-weak existential quantification over the labeling of the word. Yeah? So essentially, we have weak logic with one single strong quantifier on the exterior. This kind of distinction is meaningless for full MSO+U because this is built into the logic. So there you don't have to talk about labelings, and that's the same problem. So if you're talking about MSO+U, you can just say, I decide the MSO+U theory of the natural numbers. And here it's a more powerful result to have like this than simply deciding the weak theory of the natural numbers. The weak MSO+U theory of the natural numbers is not very interesting. Nothing happens there. And the results that are here is that satisfiability is decidable for weak MSO+U on infinite words. There's another quantifier here, which is called R. The idea is that this corresponds to lim sup and this corresponds to lim inf. In the presence of full set quantification, as in MSO+U, U and R are interdefinable, but for weak logics they're not. So there's this different result. Then there's a result which says that this is also true for trees. Weak MSO+U is decidable for infinite trees. And then there's a fresh result that I will tell a little bit about. This is a maximal result in this line of work, which is that weak MSO+U plus path quantifiers is decidable on infinite trees, and I'll tell you a little bit about this. So now I will tell you, I will start with the minimal result, and then I will tell you a little bit about the maximal result. So the minimal result is about weak MSO+U on infinite words. And it says that satisfiability is decidable, and the proof uses the automata method. So what turns out to be the case is that for this logic, there is an automaton model. And it happens to be a relatively, in my opinion, natural automaton model, which works like this. It's called a max automaton, and it's deterministic, as opposed to the previous automaton models. Therefore, it will be closed under complement, as it should be if it wants to have a logic which is closed under complement. It has a finite set of counters, and the operations that you have are, as previous, increment and reset, but there's a new operation which is maximum. If you had non-determinism, you could simulate maximum and the operation would not be necessary. But if you want to have a deterministic automaton, then you cannot, and you need to add it as an operation. And one can show that such automata, and the acceptance condition is a not necessarily positive Boolean combination of things of the form counter C is bounded. So you can say, this counter is bounded, this one's not. Implicitly, if you're saying a counter is bounded, that's saying lim sup is smaller than infinity. So you're not going to be able to say anything about lim inf. And this kind of automata will not capture lim inf, so that's one of the weaknesses of this model. And that's why the R quantifier is introduced. And the results are that max automata have exactly the same expressive power as the logic, and they are decidable by, for instance, one of the ways to show it is that they can be translated into omega bis automata, which are decidable. Okay. So that's one of the results. So if you have weak MSO+U, you have natural deterministic models. They well behaved, and they're decidable, and it's a relatively good logic. One thing I'd like you to observe is that, for instance, if you're talking about infinite words, it is well known by determinizing parity automata that weak MSO and full MSO have the same expressive power on infinite words. Therefore, this logic is an extension of full MSO on infinite words. Okay? Now, here's something that I'd like to observe, which is maybe not obvious. On infinite words, MSO is equal to weak MSO, but when U is added, this is no longer the case. This is a bit unexpected. And the reason is that the U quantifier goes into interaction with the full set quantifier, and strange things start to happen. So this is much more powerful than this, already on infinite words. And now I'd like to tell you a little bit about this new positive result about weak MSO+U with path quantifiers. So what is this logic? It's a logic for infinite trees, and what can you do? You can quantify over nodes, as usual in first order logic. You can quantify over finite sets of nodes. This is the weak part. You have the U quantifier, so you're allowed to say that sets are bigger and bigger. And here is a feature which is, I think, natural for infinite trees, which is quantifying over paths. Now, by path, I don't mean a chain. So a path cannot have holes in it, okay? It's just a full path, okay? So you're allowed to quantify over paths, which is something like this. And this is a decidable logic, and this is the result from this here. And I would like to try to convince you that it can be maybe useful to model something. So here's an example. Suppose that you have a game with a finite arena, like as in parity games, okay? But your winning condition, say for player box, is definable in weak MSO+U on infinite words. So you get a sequence of positions, and then your winning condition says something like, blocks of this position have unbounded size. Don't try to read this particular game, it doesn't make any sense. So here, if you're in this position, you immediately have to leave it, so you will have at most one consecutive position of this type. So there's no way you can win with this condition. But you see the idea. You can have winning conditions like player one can make sure that this kind of thing is visited more and more often, and that kind of thing is visited a bounded number of times, and you can quantify over that. So suppose you have a game like this. and you want to solve it. So you want to know who wins, okay? And using this logic, you can decide this using a very brute force approach, which is the same as trying to decide who wins a parity game by using MSO logic over the infinite tree, which is as follows. It's a finite arena, but you can unfold it into an infinite tree. This does not change the winner. It might change the notion of positional strategy, but I don't care about that. The winner is the same. Now, the unfolding of a specific game with a finite arena is definable in logic. I mean, you have a weak MSO logic. All you have to say that every white node has a red child and a yellow child and that kind of thing. And then you just formalize the existence of a winning strategy. So you say a winning strategy for player box, and you just formalize it the usual way. It's a choice, it's a strategy, so you choose an outgoing position for every box-owned node, such that for every path, so for every strategy of the opponent, for every path here, the winning condition is satisfied, so you, on this path, you execute a formula of weak MSO+U, and you can do this. So you can just, the set of winning strategies is definable in weak MSO+U, because if somebody gives you a winning strategy, you just write the definition of a winning strategy in the logic, and you can do that. So you can decide who wins. You can decide whether or not box has a winning strategy. Yes? So that's the difference, that it's satisfiability. So you have, the formula does not input this. It doesn't input the unfolding. It inputs the whole thing. It inputs this. It inputs the tree together with a strategy. So that's this existential quantifier on the exterior that you have for free, and you use it here. Okay, but you have to be careful. You can only use it once. You can't complement it, and so on. So that's one thing you can do. And then there's several problems that exist in the literature, which can be directly encoded into this logic. So that's why I say that path quantifiers are a natural thing that you might want, and as you shall see in a moment, full MSO+U on infinite trees is undecidable. So it seems that path quantification is closer to weak quantification than second order quantification. But that's just an interpretation. Okay? So these are the positive results. And now what I would like to tell you a little bit about. How much time do I have? So it turns out that when you're studying U and when you're studying asymptotic behavior, you have to deal with topology. Now, there's a lot of people who do topology in our group in Warsaw, and I always figured that they're kind of, you know, harmless or maybe harmful, but not useful people. But I was forced to change my mind. So it seems that this topology is not a way of generating, it's not just a way of generating meaningless questions, but it has actually, it can be applied to things. Well, just another stupid opinion that I had to throw away. So topology. What about topology? So we're going to be talking about topology on infinite words. So this is the distance. I mean, you've mentioned this. This was mentioned here several times, but I'll do, I mean, implicitly. The distance between two infinite words is the inverse, or the you can take the exponential here. It doesn't affect the topology of the first difference. So two words are close if you have to wait a long time before they're different. And this is a very well-behaved topology on infinite words. If your alphabet happens to be 2 letters, then it is the same thing as the Cantor space. It is, for instance, compact, and here it's important that you use finite words, because for finite words it's not compact. You have to make profinite words to make it compact. And the thing that you study in topology is you measure the complexity of sets. So from the point of view of the Borel hierarchy, the simple sets are the open ones, and the closed ones are on the first level. And then to proceed to the next level, you take countable union. So this is the Borel hierarchy. You take countable union, and then complementation, countable union, complementation, countable union. That's how you proceed in the Borel hierarchy. Okay? And but the hierarchy that will be more important for the rest of my talk is not the Borel hierarchy. It's something that is far more powerful, which is called the projective hierarchy. Maybe, never mind this. It's something far more powerful, which is called the projective hierarchy. And the projective hierarchy is the basic operations are complementation, as in the Borel hierarchy, but also images under continuous functions. So projective images, projection under continuous function, which corresponds more or less to quantifying over infinite sets. So you start at the very base, you start with Borel sets, and the zero, the level, it's called the bold face, because you can see this is bold face. This is not, at least I hope. Here it's not clear, but it's supposed to be bold face. And the upper index is also, so I don't know what happens if this is 2. I don't know. So the 0 level is the Borel sets, and then you take a continuous image, you get the first level, so this is continuous images of Borel sets. Then you have the complementation of those, and then you take the continuous image, and this is the second level, and so on. Okay, so this is the projective hierarchy. And to get an intuition of what it means, the idea is as follows. You are on the nth level of this projective hierarchy, if you can be defined, whatever that means, by a formula which looks like this. You have small quantifiers here, and they don't count, and you have big quantifiers. Now, the small quantifiers which are not counted, so you only count the big quantifiers. The small quantifiers, they range over countable sets. So if it's a word, for instance, you can range over positions, or maybe pairs of positions, or maybe finite sets of positions. This is a countable quantification. And this, you don't care. This is like this is good for Borel to count, you know? But if you're projective, you can do it as many times as you want. The big quantifiers are the one that you care about, and they range over an uncountable domain, such as sets of positions, infinite sets of positions, or infinite sets of pairs of positions, and that's what you want to keep track of. So that's the idea. You are on the nth level if you have n strong quantifiers, and the weak ones you don't care. Okay? So why am I telling you this? So here's a result which was proved by Michał Skrzypczak and Stefan Hummel. This is the projective hierarchy. So at the very bottom, you have the Borel sets. And it is not difficult to show that, for instance, the omega BS automata that I mentioned previously, they're Borel. They're even very low, like on the third level of the Borel hierarchy. But then you have the first level of the projective hierarchy, the second, and so on. It's an infinite strat hierarchy. As opposed to the Borel hierarchy, it's just indexed by normal numbers. It's not indexed by ordinals. So it ends at omega. And then what Stefan Hummel and Michał Skrzypczak proved is that for every level of the projective hierarchy, you can define an MSO+U language of infinite words which is complete. So that means you have MSO+U definable languages of infinite words which go arbitrarily high in this projective hierarchy, so go way beyond omega BS. And so what does it mean to be complete? It's like for Turing machines, but the reductions are continuous functions. So that means that for every language on this level, there is a continuous function which reduces it to a weak MSO+U, not weak, but MSO+U language. And this turns out to be quite significant, more significant than I originally suspected. And as you will see, it will play a role in the undecidability result. One corollary, which was already observed in their paper, is that MSO+U does not admit any automaton model, non-deterministic or maybe even alternating, such that the acceptance condition is projective in this hierarchy. The reason is that if you're dealing with this really powerful hierarchy, non-determinism just makes you go up one level, and alternation maybe 2 or something. So that means that there's no chance for an automaton which has anything to do with counters in some understandable way. Mm-hmm. Now, this result will turn out to play a role in the undecidability thing. So now the last part of my talk is about undecidability. So this is a new result, together with Tomek Gogacz, Henryk Michalewski, and Michał Skrzypczak. So Henryk is a topologist. The topologists are the disease. You just can't. In Warsaw, at least, you can't avoid working with them. And the result is this. Why do I say it's not decidable? Because the proper statement is as follows, that it is undecidable, assuming that there exists a projective ordering on the counter space, whatever that means. And I never knew it would come to this, that you would have to, you know, you have a logic, it's combinatorial, you know, verification of systems or whatever, you know, resources bounded something, and then projective ordering on the counter. But it turns out that in order to prove this, we need this, you think of this as some set theory mumbo jumbo. We need this assumption. And what is this assumption? It's a little bit like the set theory P equal to NP, P not equal to NP. So a corollary of this result theorem here is that there is no algorithm which decides MSO+U on infinite trees and has a correctness proof using the axioms of set theory and choice. And why is this a corollary? It's because this assumption, this set theory mumbo jumbo, it happens to be something that's consistent with the axioms of choice. So if set theory has a model, then it has a model where this mumbo jumbo is true, and therefore MSO+U is undecidable in that model. So at least in some models of ZFC, MSO+U is undecidable. I think that in all of them, but I don't know how to prove it. I mean, certainly it says that it's not decidable in any meaningful way. Okay? I never knew I would be involved in things like this. I would try to, in my last several minutes, try to give you a little bit of ideas about why this is the case and why do you need to invoke such crazy mumbo jumbo. And here's the idea. So the proof, it's actually, most of it is very simple. And I think in the 5 minutes I should be able to include basically all of the new material in this proof. So consider the following logic. Now, it is evaluated over 2 to the omega. So the domain is all infinite paths. So it's a little bit like the real numbers. It's a counter space, okay? So the Rabin tree, the domain is finite paths. So here the domain is infinite paths, okay? I call this logic projective MSO, and what does it do? You can quantify over individual paths. That's the first order quantification. You have a predicate which says that this path is lexicographically before this path. That's the basic predicate you have. And here's the projective thing. For every fixed n, you can quantify over a set of paths as long as it's in the nth level of the projective hierarchy. So you're not allowed to quantify over arbitrary sets of paths. But you're allowed to quantify over sets of paths as long as you specify beforehand what their level in the projective hierarchy is. And some sets of paths are not on n level of the projective hierarchy. So there are some sets of paths that you will never be able to quantify over. Okay, this is the logic. Now, the results are as follows. The first one is, assuming this set theory mumbo jumbo, this logic is undecidable. That's result number 1. And result number 2 is that this logic, which is up to mumbo jumbo undecidable, can be reduced to MSO+U on infinite trees. Okay, so assuming the set theory mumbo jumbo, MSO+U over infinite trees is undecidable. And so what is the reason for the 2 theorems? So the first one is basically appeal to the authority of Schelach. So in his famous paper, The Monadic Theory of Order, Schelach has this famous result about the undecidability of MSO on real numbers. What he proves is a stronger statement is that MSO is undecidable over the counter space, which is a definable, MSO definable subset of the real numbers. So this is what he proves. And this is almost projective MSO, except that what Schelach is allowed to use, he has one quantifier which quantifies over an arbitrary set, and we have quantifiers which quantify only over projective sets. And so our logic is weaker in the sense that it's, you cannot quantify over arbitrary sets. And if you look at Schelach's proof, he quantifies over strange sets. They're not projective in particular. No way to, there's no reason why they should be projective. Actually, he quantifies over one set. But this one set is strange. And that's the whole mystery of it. So what we did is we plowed through this proof. And then we discovered that we could modify it to get theorem 1. And our modification said that you don't really need full quantification as long as you have this strange assumption. Okay? So that's theorem 1. Now, the rest of my talk, the several minutes I've got left, I will try to tell you about theorem 2. And this is relatively straightforward. It's how to reduce this projective MSO theory of the Cantor space, where you can quantify over sets of paths, to the MSO theory of the binary tree. And how do you do that? So if you want to simulate the first order quantifications, quantification over paths, that's straightforward. Because a path is just a set of nodes. Yeah? It happens to be a totally ordered set of nodes, but it's a set of nodes. So first order quantification you can simulate by second order quantification. So far so good. But this is a short-term strategy. Because now if you want to quantify over a set of paths, then how do you do that? That would be third order quantification. Set of sets of nodes. That's not clear how to do. And here's the whole point of that it's projective. And this is where we're going to use it. So let's use our assumption that it's projective. So as we know, by the Skrzypczak and Hummel result, for every level of the projective hierarchy, such as this one, there is a complete language which can be defined in MSO+U. Okay? So if you want to quantify over a projective set in the nth level, you don't do it directly, but you quantify over a continuous reduction. So instead of saying there exists a set on this level, you say that there exists a continuous reduction, because completeness means that every set here admits a continuous reduction to Ln. So you say, instead of quantifying over the set, you quantify over the continuous reduction, and instead of using the set X, you use the pre-image of F for this thing, by assumption of being a continuous reduction. So that means that instead of saying I belong to X, I say the continuous reduction maps me to this language. So that's all you need to do. It's my last slide. Okay? How do you quantify over a continuous function? This turns out to be much easier. Why? Because what is a continuous function? A function from paths to sequences in over some alphabet is continuous if and only if it looks like a tree. So that means that there is a labeling of the standard Rabin tree by letters of the output or possibly blanks. So if you can just label the whole tree of all possible paths with labels, such that you don't use blanks too often. So on every path you see non-blanks infinitely often. And for every path, the value of a path, so maybe I draw the path here. So for every path, so this is path 0, 1, 1, 0. If you want to know the value of the path under the function f, all you have to do is just read the labels into the limit. That's a continuous function. It just follows immediately from the definition of a continuous function. So instead of quantifying over a continuous function, I can quantify over this. And this is something I can do, because this is just a labeled tree. So essentially, I just quantify over one subset per letter of A, and I can do that. So I'm allowed to quantify over continuous subset. And then, once I have that, in order to test if this path belongs to the limit, I just read the whole word labeling here, and I run the MSO+U, and I run the MSO+U formula here for this language Ln. So that's how you use the continuous function. And that's the end of this result. So you have undecidability, and you have to use this, at least that's what we use, topology. I don't know if it can be avoided. And I don't know if it's unconditionally undecidable. This I don't know as well. But it's sort of, there's no sense to work on this problem as to come up with algorithms anymore. So that's all I have to say. As I said, this is not known. Here, the trees were used a lot. So that's maybe for that reason this is decidable. On the other hand, if you look at the reason why these languages in MSO+U go very high up in the projective hierarchy, if you look at these languages, it turns out that they use some sort of encoding of trees into words. So that's an argument why this might be undecidable. And which way we'll go, I don't know. Okay, so that's all I have to say. Thank you.